Hi, so today we're working on Unit 2, Lesson 3, where we're talking about polynomials in factored forms. We're going to take a lot of those things we learned yesterday, those different relationships about end behavior and about increasing intervals and turning points and so on, and trying to look more specifically at functions and how they are related to their equations. So let's start with the idea of the multiplicity. This is another new term to know. The multiplicity is the number of times a root or a factor appears in the equation. So just a very quick example, if we have x plus 1 times x minus 2, you know that this makes a quadratic. It has an intercept here at minus 1, and it has an intercept at plus 2. And if we add a second factor here, another x minus 2, okay, this is going to change it into a cubic. So it changes it into a cubic. And it also changed the behavior of what the function did here when x was equal to 2. Previously, if you looked, the function goes straight through x equals 2. It goes from negative to positive. It changes signs, we would say. If you add a second x minus 2, then it actually doesn't change signs anymore, right? It comes down towards 2 and then bounces off. And so kind of what we're trying to get at today is what is this bouncing off effect and what's responsible for it. So the first thing to talk about is the idea of multiplicity. And it simply means the number of times the factor is repeated in the function. So each factor has its own multiplicity. So just to go back to here quickly, we would say this is an order 2 root. The reason because it shows up twice and it shows up as a bounce. This is an order 1 root because it only, this one over here is an order 1 root because it only appears one time in the equation, and if you look, the function just goes clean through the x-axis. One side is positive, one side is negative. The order 2 root, you have both sides with the same sign. It's not actually changing signs, it's just bouncing off. So each root, it has an order. So it's not like your function is order 3. Your function, it would depend on each root. So for instance here, this would have an order 1 root at 2 and an order 1 root at minus 3. So write the factors that are repeated an odd number of times. X equals 2. X equals 2, and also x equals negative 3. Remember, a factor is a number that would make the bracket equal to 0, because of course when you're multiplying numbers together, if either of them are 0, then the whole thing is 0. So a factor would be the number that makes the bracket equal to 0. In this case, you could see the number would be 2 or negative 3. Here there are none. There are no factors that repeat an even number of times because each one only shows up once. And when we look at the x-intercepts of this one, so x minus 2 and x plus 3, so f of x equals x minus 2 and x plus 3, you see that instead of there being an order 2 root like last time, there's just an order 1 root here and another order 1 root over here. So they repeated an odd number of times, once each, and the behavior of the function is to just go cleanly through the x-axis at those two values. Okay, so determine the x-intercepts. Again, x equals 2, x equals negative 3. And write the x-intercepts where the graph touches the x-axis and turns around. That never happened. Both of these x-intercepts go through the x-axis and continue on to the other section of the graph, so at no point does it bounce off and come back. Okay, the next one. We have factors that repeat an odd number of times. The x plus 2 is a factor that repeats an odd number of times. So again, the factor would be, the roots, would be minus 2. The factor is actually x plus 2. Write the number of factors that repeat an even number of times. Once again, there are none. Determine the x-intercepts. So again, what makes each of those brackets 0? X equals negative 2 is one option, and x equals 3 is the other option. Does the graph turn around? Does it bounce off the x-axis? I would predict no, because we have nothing here that repeated an even number of times. We have no even order roots. However, let's check just to be sure. So we'll go x plus 2 cubed and x minus 3. So we have x plus 2, which is a factor that repeated 3 times. So x plus 2, x plus 2, x plus 2, and then x minus 3. Again, we'll just zoom this out a little bit to see. This is not an order 1 root anymore. Actually an order 3 root now, because the factor appeared 3 times. And actually, if you look closely, it seems to show the behavior of a cubic, right? Like right about here, it kind of looks like a cubic, right? This sort of it's a flat tangent, but it doesn't it's not a turning point. So you kind of see the way that the order of the root kind of controls what the function looks like at each x-intercept. If you examine the order 1 root over here, right, you see that, well, this kind of looks like a line's behavior in this region, right? It's just a straight line that goes through the x-axis. So the order of the root kind of determines the shape that you should expect the graph to look like at that particular x-intercept. So again, the zeros where the graph touches and turns around, again, there were none. Here we have factors that repeat an even number of times. An odd number of times is x minus 4. The even number of times is x minus 1 and x plus 1. Both of those factors repeat an even number of times. For roots here, we'll get x equals 4, we'll get x equals 1, and we'll get x equals negative 1. Again, those are the 3 values which you could sub into that equation and produce a value of 0 overall. So just quickly, we'll just copy this over to GeoGebra. We'll paste change f of x to this function. And so just to pull this out a little bit, okay, now we have some different looking stuff. So we don't have any order 3 roots because no factor repeated 3 times. We do have an order 2 root here. Okay, oops. Have another order 2 root here. Okay, so just to stretch this out a little bit, we could see there's an order 2 root at minus 1. You can see if we just zoom in a bit, the function bounces off the graph there. It also bounces off the x-axis, bounces off the graph, bounces off the x-axis. Okay, so here we're looking at, this is an order 2 root, this little section. And if you kind of look at it, it kind of looks like a quadratic, right? A parabola, where a parabola sort of bounces off, again, just in that local neighborhood, right? The whole function obviously looks nothing like a parabola, but this particular region does, because it's an order 2 root. And this particular region as well kind of looks like a parabola for the same reason, right? This one over here, it looks like the same sort of shape where it's bouncing off the graph, bouncing off the x-axis. So again, how to draw an x-intercept? If it's order 1, go straight through the graph. If it's order 2, bounce off the graph like a parabola. If it's order 3, go through the graph the way a cubic does. Kind of flatten out, hit the x-intercept, and then keep going in the other direction. Okay, so for this last, so again, the x-intercepts where it bounced was x equals 1 and x equals minus 1. The two values that were repeated an even number of times. So quickly, the last time, an odd number of times would be x minus 2, an even number of times would be x plus 2. The x-intercepts would be x minus 2, x equals negative 2, and x equals regular 2. And the one that's going to bounce, we can predict, will be at x equals negative 2, because that is the factor that is repeating 4 times. So let's draw this one just so we're confident. So it was x minus 2 to the 4 and x plus 2 to the 3. And I've got that backwards, sorry. It should have been x plus 2 to the 4 and x minus 2 to the 3. And if we look at this one, okay, so this one is now an order 4 root. And if you look at it, you know, it looks a lot like a quartic. It's quite flat, but it does turn around. Okay, that's what the quartic did. Here over here we have an order 3 root, and again you just look at looks exactly like the cubic does, right? It rises, flattens out, but then continues to rise. Okay, so an order 4 root and an order 3 root would be what we get there. The order 4 root is a bounce, the order 3 root is not. So the order 4 root was the one that repeated an even number of times, so x equals -2 is what gives us the bounce and the turnaround. So to summarize, the graph of a polynomial function touches the x-axis and turns around at every x-intercept that has an even multiplicity. What we're going to say is an even order root. Okay? The graph of the polynomial crosses the x-intercept if you have an odd multiplicity. Again, an odd order root. Well, the other thing we might say is the factor repeated an odd number of times. Okay? The graph will cross the x-axis at any single root. For odd ones. Yeah, any single root, of course, isn't. Sorry, I'm just trying to figure out what this means. An odd, a single time is an odd time, right? There's only one, so it will cross any time there's a single root. Okay, how do you sketch a polynomial? So that is our bigger skill today. Is how do we now know a lot. We know how to get the end behavior. We know how to deal with the roots. So now we have everything we need to sketch. Now we're not drawing a perfect graph here. Notably, we're not really going to figure out, for example, on this graph, how you would find this local min. This local min down here at like -135. We're not going to do that. So we're going to figure out how to get the root, how to get the y-intercept, how to get the other root, and how to get the end behavior. That's what qualifies as a proper sketch in advanced functions. So the first thing to get when you're sketching a function is the y-intercept. Very easy to do. You simply plug in the value of 0 and figure out what y value goes with it. It will always look like 0, y, because whatever y is, when you plug in 0, that point is the y-intercept, and generally speaking, it's pretty easy to find. The x-intercepts are a little bit more difficult. Keep in mind that for the time being, we are talking about functions in factored form, so they will always look like the way they do up here, and therefore you'll be able to find the x-intercepts fairly simply. You just need to sort of analyze them bracket by bracket. Once you have the x-intercepts and the y-intercept, you are now able to think about the end behavior. Remember, the end behavior is the concept of where will the arrows point at the far right and far left of my function. So this is just the chart from yesterday reminding you that the degree of the function and the leading coefficient together determine all the different possibilities of what you might need to draw. Odd functions, recall, they either start low and end high, or the other way around, start high and end low. An even function starts and ends on the same side, so they either start and end high or start and end low. If you need to, you can check values in between your x-intercepts, okay, x values in between the x-intercepts, and check to see if they're positive or negative. This will help you confirm that the picture that you have drawn is correct. You're going to notice in this kind of work that you know more about the function than you need to know, so sometimes you're going to get information that's redundant, but that's a good thing. It just means that you are on the right track. You have information that confirms what you already think. Again, there are multiple ways to go about these questions. There are steps that reinforce one another, and there should be a good reason that you're confident that your answer is right by the time you get to the end, because all of these things kind of work together and cohere into one picture. So this is just an example of what this process would look like. Suppose I'm looking at the function x minus 4, x minus 1 squared, and x plus 3. I know where the x-intercepts are. There's an x-intercept at -3. That's what would make this bracket 0. There's an x-intercept at 1. That would make this bracket 0. And there's an x-intercept at 4, right? That would make that bracket 0. Now, if I were to test a number in between each of these regions, it could help me figure out, where the function's going to be. Because remember, a function can't go from positive to negative unless it goes through an x-intercept first. So that means if a function's positive in one of these regions, it's positive for the whole region.